Welcome, students, to the captivating realm of physics, where curiosity meets discovery. As we embark on this intellectual journey, I encourage you to explore the wonders of the universe, from the smallest particles to the vast cosmos. I invite you to view our latest video, which delves deeper into this fascinating subject. Kindly subscribe to our channel for ongoing insights and discussions that will ignite your passion for learning. Together, let us uncover the mysteries of nature.
Now you are all welcome to the world of physics to explore more. Dear students, in this video let us study about the oscillations in LC circuits. The first case, energy conversion during LC oscillations, and then conservation of energy in LC's oscillations. Finally, analogies between LC oscillations and simple harmonic oscillations. Now let us study about oscillation in LC circuits. First of all, let us study about the energy conversion during LC oscillations. How these LC oscillations are produced. We have already learned that energy can be stored in both inductors and capacitors. In inductors, the energy is stored in the form of magnetic field, whereas in capacitors, it is stored as electric field. Whenever energy is given to a circuit containing a pure inductor having an inductance L and a capacitor of capacitance C, the energy oscillates back and forth between the magnetic field of the inductor and the electric field of the capacitor. Thus, the electrical oscillations of definite frequency are generated. These oscillations are called LC oscillations. How these LC oscillations are generated? For that, let us assume that the capacitor is fully charged with maximum charge QM at the initial stage. So the energy stored in the capacitor is maximum and is given by the expression UE is equal to Qn square by 2C. As there is no current in the inductor, the energy stored in it is 0. That means UB is equal to 0. Therefore, the total energy is wholly electrical, and that is shown in figure 4.52a. So here. Then, the capacitor now begins to discharge through the inductor that establishes current I in the clockwise direction. This current produces a magnetic field around the inductor, and the energy stored in the inductor is given by the expression UB is equal to Li square by 2. As the charge in the capacitor decreases, the energy stored in it is also decreases, and is given by the expression UE is equal to Q square by 2C. Thus, there is a transfer of some part of energy from the capacitor to the inductor. At that instant, the total energy is given by the sum of electrical and magnetic energies, and that is given by this diagram 4.52b, this one. Then, so this is the diagram having inductance and a capacitor. So a current I flows through it. Then, when the charges in the capacitor are exhausted, its energy becomes 0. That means UE is equal to 0. The energy is fully transferred to the magnetic field of the inductor, and its energy is maximum. This maximum energy is given by the expression UB equal to LIm square by 2, where Im is the maximum current flowing in the circuit, and therefore the total energy is wholly magnetic. That is given by this 3. So here it is wholly magnetic. The energy will be magnetic in nature. Then, even though the charge in the capacitor is 0, the current will continue to flow in the same direction because the inductor will not allow it to stop immediately. The current is made to flow with decreasing magnitude by the collapsing magnetic field of the inductor. As a result of this, the capacitor begins to charge in the opposite direction. A part of the energy is transferred from the inductor back to the capacitor, and therefore the total energy is the sum of both electrical and magnetic energies, and that's given by this diagram D. Then, when the current in the circuit reduces to 0, the capacitor becomes fully charged in the opposite direction. The energy stored in the capacitor becomes maximum, and as the current is 0, the energy stored in the inductor is also 0. Therefore, the total energy is wholly electrical, and that is shown here in this E. Then, The state of the circuit is similar to the initial state, but the difference is that the capacitor is charged in opposite direction. So the capacitor starts to discharge through the inductor with anti-clockwise current, and therefore the total energy is given by the sum of the electrical and magnetic energies, and that's given by this diagram here. Then the process is repeated in opposite directions, that is given by 4.52 G and H. Finally, the circuit returns to the initial state, so that's given by A. Then, when the circuit goes through these stages, an alternating current flows in the circuit, and this process will be repeated again and again, thereby producing electrical oscillations of definite frequency, and these are known as LC oscillations. The ideal LC circuit, there is no loss of energy, therefore the oscillations will continue indefinitely, and such oscillations are called undamped oscillations. Next, we will study about the conservation of energy in LC oscillations. During LC oscillations in LC circuits, the energy of the system oscillates between the electric field of the capacitor and the magnetic field of the inductor. Although these two forms of energy vary with time, the total energy will always remain a constant. It means that LC oscillations take place in accordance with the law of conservation of energy. So the expression for the total energy is given by U is equal to UE plus UB, that's the energy due to electric field and energy due to magnetic. That's given by Q square by 2C plus half Li square. So let us consider three different stages of LC oscillations and calculate the total energy of the system. The first case, when the charge in the capacitor Q is equal to Qm and the current through the inductor is given by I is equal to 0, then the total energy is given by the expression U is equal to Qm square by 2C plus 0, that's given by Qm square by 2C. That means the total energy is wholly electrical in nature. The second case, when the charge is equal to 0 and the current is maximum, that's given by IEM, then the total energy is given by U equal to 0 plus half LIM square, that's equal to half LIM square itself. So in this case, the total energy is wholly magnetic, as the expression is given by Qm square by 2C. And in the third case, when the charge is equal to Q and the current is equal to I, then the total energy is given by this expression U is equal to Q square by 2C plus half Li square. And since Q is given by the expression Qm cos omega t and I is equal to minus dQ by dt, that's given by Qm omega sin omega t. This negative sign in the current indicates that the charge in a capacitor will always decrease with respect to time. And the expression for the energy is given by U equal to Qm square by 2C. So you can see that in the first case it's given by Q square by 2C, and in the second case also it's given by Q square by 2C, and in the third case again the expression for energy is given by Q square by 2C. So the total energy of the system will always remain a constant. Now let us see what are the analogies between LC oscillations and simple harmonic oscillations. Let us have a qualitative treatment. The automatic oscillations of a LC system can be compared with the mechanical oscillations of a spring-Morse system. There are two forms of energy involved in LC oscillations. One is electrical energy of the charged capacitor, and the other one is the magnetic energy of the inductor, which carries a current. So here the energy in two oscillatory systems are given. This is all about the LC oscillator, and this is spring-Morse system. Here the element is capacitor, for which the energy is given by half into 1 by C square, 1 by C into Q square. And in the case of inductor, the magnetic energy is given by half Li square, where I is equal to dQ by dt. In the case of spring-Morse system, the spring will have a potential energy of half Kx square, and for kinetic energy it's given by half mv square. So these are having similar formula. Likewise, the mechanical energy of the spring-Morse system exists in two forms: the potential energy of the compressed extended spring and the kinetic energy of the mass. This table 4.2 lists these two pairs of energy, that is electrical energy and magnetic energy in the case of LC oscillator, whereas in the case of a spring-Morse system we will have potential energy and kinetic energy. So by examining the table, the analogies between the various quantities can be understood, and these correspondences are given in this table for point 3. Was a charge, current, inductance, the reciprocal of capacitance, all these things are given in this table for point 3. The angular frequency of oscillations of a spring mass is given by this expression omega equal root of k by m. And here in this case of LC oscillations, the angular frequency is given by omega equal to 1 by root LC. So these are the things that we should remember in this topic.